Welcome everybody, welcome to our next topic in reactive intermediates carbene and nitrene, that is the Siemens-Smith reactions continuation. We are already discussing about the Siemens-Smith reaction. Okay. Last class we have discussed about what is the reagent necessary for this particular reaction and how the reaction goes through, that means the mechanism of this reaction, and after that we have studied few examples with different type of olefin, how that will convert into the corresponding cyclopropanes, and we have seen that how the alene, that type of molecule also can be converted into its cyclopropane derivative. Okay. So, today we will learn different variations in Siemens-Smith reagent, little bit of that, and after that we will proceed with different additions reaction with various carbenes generated with the help of transition metals. Okay. So, now the variations in different Siemens-Smith reagent, as per example we will see let us say we have this protected diol. Okay. This is a C2 symmetric diene. Okay. So, this diene, if it is exposed under modified Siemens-Smith reagent, here what they have used diethyl zinc and the methylene iodide, okay, for the generations of this modified Siemens-Smith reagent, and once it has been generated, then it gives the corresponding cyclopropane ring, that is in this case what you will get, sorry, this bond will be bold. So, what it will get, okay, and here this cyclopropane ring is this. Okay. So, you can easily understand that due to presence of this heteroatom, how these heteroatoms, here it is oxygen, is guiding the stereochemistry of the cyclopropane. In this case, it is a beautiful example. You see there are two hydroxy groups with different stereochemistry, and they are actually guiding that what will be the stereochemistry of the product, cyclopropane product. Okay. Now, in another example where it has been used vinyl silyl ether as the starting material, okay, in presence of diethyl zinc and methylene iodide, okay, as for its as a modified Siemens-Smith reagent, and the product is again the corresponding cyclopropane, okay, having this TMS ether. Okay. TMS means here, okay, O silyl group trimethyl silyl. So, I am not drawing the rest of the part. So, this is the corresponding TMS or O trimethyl silyl. Okay. This is a one hydroxyl protecting group. Now, we will see the transition metal carbene complex in cyclopropane synthesis. So far we have seen that how Siemens-Smith reagent or its modified version has changed the olefin into its cyclopropane ring or the alene to corresponding cyclopropane. Now, we will see that how transition metals or transition metal complexes, they can generate the carbenoid type species for the cyclopropane synthesis. Okay. So, overall mechanism that we can predict from here. So, if we have this metal complex and if we have this carbene precursor, let us say here it is diazo group. Okay. Now, this can easily liberate the nitrogen, okay. And if it liberates nitrogen, what it will form? Okay. Now, this can again go back to here, but obviously the olefin becomes the cyclopropane. Okay. So, we have started this corresponding diazo compound. So, in presence of metal, it will transition metal, it will liberate the nitrogen, it will form the metallocarbene, and the olefin will be converted to its cyclopropane ring. Okay. Now, this reaction, that is from the olefin to cyclopropane, that can goes via two different way. Okay. So, what I mean that when this transition metal carbene complex has been used in cyclopropane synthesis, then that follows two general mechanism. So, this transition metal carbene guided cyclopropane synthesis rather follows two general mechanism it follows. Okay. So, what are the two general mechanism? Number one is that it can goes via a 4-membered ring intermediate. So, if we have this type of complex, now we have olefin. Okay. So, now it can form this 4-member intermediate. Okay. So, this is the okay. So, once it generated, then this 4-membered ring that can decompose to the corresponding cyclopropane ring. So, this will be okay. So, what will be the next one? So, the next general mechanism could be via stepwise. That means, that if there is some electrophilic type of attack to this carbene, as we have said that carbenes are generally like electrophilic in nature. So, via an electrophilic attack to form a polar species. Okay. So, to form a polar species which finally goes 1,3 bond migrations and give the corresponding cyclopropane. Let us see how does it work. So, if you have this metallocarbene, then you have this olefin. Now, it can attack like a electrophile, like this olefin is attacking to the electrophile, then okay. So, it is having something like this. Then now, this polar species which can undergoes this 1,3 bond formation, and that gives okay. So, this is via an electrophilic attack. Okay. Here we have to keep in our mind that as this type of cyclopropane synthesis are stereospecific in general. So, if the mechanism 2 is responsible, then the product formation step that should be more rapid than that of single bond rotation. Otherwise, if this bond formation step is not fast enough, then there will be chance to rotate among this carbon carbon single bond around this carbon carbon single bond. Overall, the stereospecificity will not be maintained, but we found that in these reactions generally are highly stereospecific. Okay. So, in this case the transition metal carbenes that can form the cyclopropane through these two general mechanism. Okay. Now, we will see some of the example through these methods. If we take this Norbornadiene type of system and in presence of the carbene precursor, here the diazo ester and the transition metal complex is this CuCN here, then the product is the corresponding cyclopropane. But here one interesting thing is that there is a possibility of two different stereoisomers. Okay. One could be exo and another one is endo. Interestingly, here only one stereoisomer has been formed and that is the exo one. Obviously, this exo product is thermodynamically more stable and there is less steric interaction or less steric hindrance. That is why this product is stable and this product is sole product here, okay, or maybe the major product here. Next, if we take the diene as per example this one, okay. So, with the corresponding diazo ester as the carbene precursor, and with the copper metal, then again the product is the monocyclopropane one. Interestingly, here the diene is more nucleophilic than the its monoolefin. Okay. So, what happens when the diene is there, that can readily attack and after formation of one cyclopropane ring the reaction stopped. So, in this way you can actually control the monocyclopropanation. Okay. So, this will generate, this is called ethyl chiransen 3-mate. Okay. So, this can be further leads to one natural product that is called pyrethrine I. This is a one insecticide. Okay. This name is pyrethrine I. Okay. So, this is one insecticide. Okay. So, in this way actually this diene can react with the carbene metallocarbene and give this monocyclopropane, and this fragment has been used for further total synthesis. In another example, we will see that the molecule contains the corresponding diazo part and the olefin part, both are in one molecule. Okay. So, they are methyl, methyl, methyl. So, in this case what will happen? Previous cases we have seen that the metallocarbene and the olefin, they have reacted in intermolecular way. But in this case we have seen the precursor for the carbene and the olefinic part, both are present in one single molecule. So, this is a beautiful case where the carbene can react intramolecularly. Okay. Let us see how does it react. Now, in presence of this CuI, what will happen, that copper iodide, then there are actually two different olefins are there, but in presence of this metal iodide, what will happen, that the formed metallocarbene will selectively react with only one double bond. Okay. If you see here, both the double bond, both the olefins that are tri-substituted. Okay. So, but the product what they found, that is the 6 and 3 member ring, that is the cyclopropane fused cyclohexene. Okay. So, if you see that only this double bond, reacted. Why? Because when the carbene insert into this double bond, or when this addition is happening, that gives 6 member ring if it reacts with this double bond. So, that you will get this stable 6 member ring. Okay. Otherwise, in this case it will form very large member ring, rather than forming 6 member is much more easier. So, it reacts, or the carbene, metallocarbene, that add to this olefin. Okay. Now, further it has been converted into the another natural product, that is called cyrenene, using 2 steps, that is first selenium dioxide mediated allylic oxidations of this allylic methyl will be oxidized, this part will be oxidized. Okay. So, this part will be oxidized, and after that reductions, so that will eventually give this natural product, and in presence of lithium aluminum hydride, the reductions will occur also finally, and give the ester to corresponding alcohol. Okay. And here and this is the name is cyrenene. Okay. So, here in selenium dioxide mediated allylic oxidation followed by reductions in presence of lithium aluminum hydride gives this natural product cyrenene. This has been done by Professor E. J. Corey. Okay. So, this is one beautiful example where these cyclopropane synthesis via the addition of these metallocarbenes to the olefin leads to the natural product. Okay. Next we will see if we have another heterocycle, this is called the benzothiophene derivative and its intramolecular carbene insertions into the corresponding double bond here, what it will give in presence of rhodium complex okay, that will give this product. Okay. So, basically after forming the carbene here, that will make the cyclopropane here. Okay. So, overall these intramolecular reactions will generate cyclopropane ring. In another example, if we take this cyclopropene system, okay. This is also precursor for carbene. Now, again under rhodium complex, this will generate the metallocarbene and overall the product will be the insertion of this metallocarbene into this double bond and eventually that will give the product okay. So, after addition of this metallocarbene into this corresponding double bond, that generates this product. Okay. So, this is the transition metal based metallocarbene added to the olefins and that gives the different type of cyclopropane rings. Next we will see other different type of addition reactions using various carbenes. So, other addition reaction. Okay. As per example, if we take this system, you see here there are two double bond, one is tetra substituted, another one is di substituted. Now, if we use this dichlorocarbene as the reactive intermediate or reactive carbene here, then what will be the product? Okay. In this case, what will happen that first there are two possibility that it can react here or it can react here. As you have seen, this double bond is highly substituted and more electron rich. So, it will react with the electron deficient carbene and first give as a major product and the minor product will be So, in this case it is obvious that as this double bond is not that much electron rich. So, this is giving the minor product, whereas this double bond is more electron rich. So, this is giving the major product. Similarly, if we take only benzene, what will happen with only benzene? Then we will take the diazo ester as the carbene precursor, then under heating conditions this will generate the carbene, and what it will form? Okay. So, this haloelectrophilic carbene will generate the cyclopropane ring. Okay. Now, electrocyclic ring opening, this is one type of pericyclic reactions. Okay. The electrocyclic ring opening, that will give this 7 membered ring. Okay. So, after forming of the cyclopropane ring, it goes via the electrocyclic ring opening and gives this stable 7 membered compound, and that is one type of reactions where after formation of cyclopropane it rearranges to another product and gives the 7 membered ring containing ester product. Thank you very much.